Okay, hi everyone. We are group 2 and we are ready to give our final three-way P6 like out of order processor presentation. This is our system overview, and on the left side you can see our memory system with non-blocking associative D-cache, non-blocking associative I-cache with a prefetcher. And for the outer sections, we implemented an ARS queue with internal forwarding, which can issue memory access out of order, and a G-share predictor for the MPC predictions. And we finally implemented a three-way superscalar execution for the out of order core. And next, each of us will give the presentation of the part we are responsible for in turn, okay? For the first part, iCache and iFetch, since we are implementing three-way superscalar to fully utilize our system's parallelism, there's a paradox that the memory can only output 2 instructions per access. So, an MSHR table is implemented to alleviate this mismatch, since during this, we can access a memory without blocking like next loading, right? Okay, and another prefetcher is implemented to provide the greedy next line prefetching. Greedy here means when there is a miss for the iCache, the prefetcher will keep sending the load request to the memory until there's a jump or a flash signals. Thus, for the most cases, we can output 3 instructions per cycle. Okay, next one is predictor. Tianyuan maybe?
So our predictor takes in the MPC from the fetching unit and outputs the predict result in 3 bits and also the possible target PCs. It has 4 modules, a 64-bit BTB, a 256-bit set-string counter, G-share predictor, and also a chooser.
So for the dispatch is the module between the fetch stage and the out of order core. It is able to decode 3 instructions at a time, and it's responsible for detecting the structural hazard. It will send out a stall signal if it detects the structural hazard, and the stall signal will stall the whole front end. It will also send different decoded signals to different modules in the out of order core.
The out-of-order core is basically what P6 style like. A basic functional diagram is shown on the right. Since we are a three-way superscalar machine, each unit inside this out-of-order core has to have the ability of three-way internal forwarding. For the reservation station, it has been split to 5 smaller stacks dedicated to each functional unit. As shown in the diagram, it is actually not a stack but a FIFO style to ensure it always sends the oldest instruction available. To reduce the logic complexity, branch units and LSQ units use in-order stack, which will issue the instruction relatively in order.
Our processor 5 functional units, 2 ALUs, 1 multiplier, and 2 address calculators. A rotating random selector is embedded in the FU modules and can select 3 results to broadcast. The selector will return a busy signal to the reservation station to indicate which ALU has finished calculation but yet not be broadcasted by CDB.
We have a very simple LSQ because we have a fancy Bcache with very high hit rates. The LSQ only has a store queue without load speculation just to ensure the precise state store, and the LSQ is able to do the load to store forwarding to forward the data if the address hits, and we have logics to support the non-blocking cache, and the LSQ is able to handle 2 instructions at a time, one from the functional units and another one from the Dcache, either it's a pending load or pending store. Moreover, there are pipeline registers embedded in the LSQ, and the data is going to be sent to CDB after the pipeline. And we have a very loose stall so that we can keep sending instructions to the Dcache while we are sending data to the CDB.
Okay, for the Dcache part, to strike a balance between the CPI and the clock cycles, we finally take the associativity of 2 we also implemented MSHR for the non-blocking implementation, but the thing is we added the internal forwarding and merging functions to the Dcache MSHR, which means if there exists previous load or store instructions which is in the flight, since they are missed, right? So the later instructions handling the same address will be internally forwarded or merging according to is a read after write or write after write or something like that. And we implemented the write allocate and write back strategies here. It's really important for us since by doing so, the Dcache will only write to the memory when one block is retired from the Dcache. And it's like reduce the Dcache by occupying the memory bus system. So it makes our aggressive iCache prefetching strategy possible and efficient. Okay, that's all.
Okay, this is the analyzed part of out-of-order core. We have tried different depths of rotor buffer. Rotor buffer depth of 8 could synthesize at 8 nanoseconds, depth of 16 at roughly 10 nanoseconds, and depth of 32 at 12 nanoseconds, respectively. And every CPI of these 3-2 setup are at 2 to 3, and we finally choose 16 because when it's bigger than 16, it has very little performance increase. And since out-of-order core stuff isn't on the critical path in the end, and we have run out of time for debugging the correctness, we haven't tested the different setup of reservation station depths, but simple analysis shows that when the reservation station entries are bigger than 5, it won't be the bottleneck of the whole core.
An interesting analysis is the stage number of the multiplier. The left graph and the right graph show the CPI of different stage pipeline by testing assembly files and C program files. Combining with these two graphs, we can draw conclusions that the A-stage multiplier can more fully exploit instruction level parallelisms than the other two due to its high latency.
Here's the data retrieved from the predictor. From no predictor to the G-share implementation, we can see a big improvement on the overall accuracy, especially for those long programs like outer product. For the hybrid design, it provides reasonable improvement on those short programs. However, for the long programs, the improvement seems trivial. That's why we decided to simplify our design to a simple G-share implementation on our final submission. Combining the results from the average CPI and average execution time, it seems a good trade-off.
Okay, as for the prefetching strategy analysis, thanks to our write-back and internal merging Dcache implementation, our greedy prefetching can boost the performance by up to 25%, and in most cases, our greedy next-line prefetching can outperform the typical prefetching next-line prefetching. Okay, I think that's all. Thanks.